So please, so I don't skip this for the sake of objective question. Whenever you hear charging by contacts, I will do this one when I'm painting magnetism. Whenever you hear charging by contacts, it simply means situation where you are rubbing to cause friction. Rubbing to cause friction. And I've told you that the practical examples we use on campus is situation where they always tell you about carbonites, or they tell you about plastic, or they tell you about glass. Lecture examples we have on campus. I now said, this is because of objective question, that's why I'm doing this. I now said that carbonite is like rubber that is strong. Plastic, like you need to apply pressure to before you can break it. But you see that glass, if you are not careful to break it, that is why I said consider this naturally. All these things are insulators, but consider it with the same mindset that you look at metal. Anytime you say something is a metal, it simply means that thing is resisting in a positive state. This resistance is in a positive state. Metals give electrons out to stay positive, it exists positive. So for that reason, these ones are strong like metals. I say that they are positive when you've not rubbed or engaged in friction. They are positive before being engaged. This one now is easy to break. I look at it as a non-metal, but all these things are insulators. But because I know that non-metals exist in a state of negative. So now, the question can come, they tell you, carbonite with 4 gives what type of charge? What they are asking you there is not the force charge, but the carbonite charge. So for that reason, what you need to know now is that since carbonite exists in positive, if it gets rubbed, it will give off the positive and not take negative. The same thing with plastic. Since it exists as positive naturally, if it now gets in contact or gets rubbed, it will give off the positive and not stay negative. So any person that asks you carbonite with 4, carbonite with 6, carbonite with whatever, plastic with whatever, is simply asking you what will be the charge on that thing when it has been rubbed or when it has made contact with another thing. So the answer will simply be that positive will not turn to negative. So the answer there is that what the type of charge there you will have for plastic will be negative. The type you will have for carbonite will not be negative as well. So that's the answer you should give them in that objective question. You must say it. They don't joke with it. Why for glass? Since it's existing as negative, on contact or exchange, it will give off the negative and not take what? Positive. So this will change to positive. So this thing I'm telling you now, very important. If you go to your textbook, most times, most people misplace it. It's now when you study, research, you confirm what I'm saying. Because I know that there's a part in your textbook is correct, but there's a place in your textbook that it needs to be correct, but they made a mistake there. They misplaced it, they interchanged it. So it's important to always remember this. So you don't enter the hall and make the mistake of interchanging it. Know that. So for contact, by contact, simply have it in mind that whatever is strong, you consider as staying in positive state. Whatever is weak, consider as in negative state, so that on engaging. So this one will have negative charge, which is minus 2. Minus 2. And this one will end up having plus 2. Okay, let's move to charge conservation. I want to clean. Can I clean? Anytime as a student, remember I said anything you see that has induction to it is more of when you're doing magnetism. I told you that when you hear inductor, it deals with magnetism. When you hear capacitor, it deals with electricity. Now, anytime you hear conservation, it's not just in physics, anywhere at all. What they are telling you is that it cannot be lost. That something cannot be lost. That is what anywhere, if they tell you mass conservation, energy conservation, this one conservation, they are just telling you that this thing cannot be lost, but can change form. You get the point now? Whenever you hear, for example, energy conservation, That law practically talks about energy can neither be created nor destroyed, but can be changed from one form to the other. If you come to mass, they are telling you that mass can never, that is, the amount of matter in the body cannot be created or destroyed, but can change from a form to another. But when it has to do with charge, what they are saying in charge is that charge is not lost, but rather moves from positive to the negative. If you notice it, when you have a positive charge and a negative charge, at the end of the day, if it's moving from positive to negative, it is trying to maintain a neutral state where you have balance. That is just what charge conservation is talking about. So anytime you hear something having conservation without defining much, just have it in mind that that thing is simply talking about a part of it that cannot be lost or can change. So it can either change from positive to negative or from negative to positive. And remember, how does it change from positive to negative? It changes from positive to negative simply when charge moves from the positive, it terminates at the negative. Is it not true? And if that be the case, it simply means that when you enter something like capacitor, the belief is that charges always move from positive to negative. But when we start doing capacitor, you will see that there is a reason why in real life they tell you that it's not positive charges that are actually moving, but electrons. But in physics, we believe that it's the positive that is moving. Reason being that for a capacitor, the creation of that field on the inside where positive is moving, it cannot cross that inside because inside a particular surface, a particular conductor, we say that the electric field there is zero. So if that be the case, and also protons are heavier than electrons, so for that reason, electrons will have to travel faster, and electrons will have to leave the surface that has the negative, which is down, and not the up. The up passes positive, comes to the middle, comes to the negative. So it's the negative that is allowing that passage. While for the positive, you judge the middle where it is zero. When we get to capacitor, I'll still illustrate this proper. But what I'm trying to get to your point or to your head is that charge conservation talks about the fact that charges cannot be lost, but rather can change. Is he being attracted or is he being repelled? That's just what that point of conservation talks about. Now for coronal discharge talks about the air around, the air around charges or the air around surface of charge getting ionized. The air around surface of charge getting ionized. The air around surface of charge getting ionized. What that means is that if, for example, we know that I don't want to draw anything. I know that it's very simple. You're not going to the part where I'm drawing. So what that means is that if, for example, I have surface, I told you in our first class that every charge you have on the surface, or every charge you have in a particular system, tends to move up to the surface. That's what I said. And if it moves up to the surface, it wants to get to the point that is sharpest. So you see that it's more like where you are having an imbalance because all of them want to escape. The same thing with the chemistry you will learn this semester. When they start teaching you solutions, vaporizations, surface tension, if it comes to the top, it gets heated, the kinetic energy, the one up will move down. As it gets heated, it will move up again, then it will come down. Then at a point where it reaches saturation, whereby the pressure inside that container is the same with the atmosphere, you now have boiling point. It's part of the things that will teach you this semester. But the same concept is still what we have here. If I have, for example, let's say this is scissors. Let me use this to make it come to should I say you're understanding better? If I hit these scissors up, we are saying that if this is positive charge, that at this point that is the sharpest, notice that this is the smallest part here, the steepest, that on this mouth part, that I will have more than just one charge. All the charges we want to gather around this upon is the smallest. So all of it we want to gather here. Not like charges are not moving around. But what it's doing is that in itself, it feels that if there's any opening, or any need for you to contact with another, it can easily escape through this. Because it's easier for it to escape on this than on this other side. So that See, this one I'm explaining now that charges gathered at the steepest point or the sharpest point is what we call action of point phenomenon. And this action of point phenomenon is now what creates the air around this region, the air around this particular region, the air around this particular region, we end up getting ionized. That is why sometimes if you are doing something, or if you are practicing, or if you see some persons doing certain things, you will see something like blue lights around that region. Like you now call it, normally you call it spark. That thing you call spark is what we call coronal discharge. So it will light up this region, that air region. So what that is doing is that it is ionizing the air around that region. So we say that coronal discharge is simply the ionization of air around charges. The ionization of air around the ionization of air, or air ionization of the ionization of air around charge surface or charge region. I don't know how to put it, but I believe you understand the whole concept. So it's self-explanatory. The ionization of air around charged region. The ionization of air around charged region is what we call coronal discharge. And this is as a result of action of point phenomenon. And this is as a result of action of point phenomenon. You see how these ones I'm doing now? So many persons are not here. But this thing I'm doing now will help you with objective questions. So there are some objective questions you very well know that it's not calculation. So all those objective questions that don't involve calculation, once you see it, you see that all these things I'm saying will remind you the answer to pick there. So let's move to permittivity of the medium. Permittivity of the medium. When you hear a medium's permittivity, from the word permission, you get permittivity. So it's simply talking about the ease of movement of electric field lines. Then we use electric field lines. I want to give it to you how you might see it in your textbook or some textbooks. Then I will now explain it better. The ease of movement of electric field lines. How easy it is for electric field lines to pass through electric field, or how easy it is for electric field lines to pass through a charged region is what we call permittivity of a medium, or permittivity of that. Let's use it that way. Permittivity of medium. The ease of movement of electric field lines is known as permittivity of a medium. But me, I hate that definition. There are some things that if I read inside textbook, I feel is stressing me. So first of all, what creates electric field? Maybe it's a charge. Is it not true? So if it's a charge that creates electric field, that means that permittivity is simply how easy it is for charges to pass through electric field. How easy it is for charges to pass through in an electric field. That is what permittivity is. How easy it is for charges to pass through in an electric field. That is permittivity. So sometimes they just put it the way they put it, but when you go through it, you still see that the breakdown is simply by what brings about that thing. So how easy it is for charges to pass through electric field region or electric field around electric field is what we call permittivity of a medium. Now it's not just something you note like the rest. The rest you can note it and know that you just write it as English. But for permittivity of a medium, you need to note that there are mathematical relationships here. Permittivity of a medium is simply given by sometimes E like this, sometimes you see like this, sometimes you see like this, sometimes you see like this. But I will use this one. This is different from when I write this thing for electric field intensity. Look at this. You will say it's E, but note it that this is how they put it. And sometimes this E, when we start doing capacitor, this E is also referred to as K. This E is also referred to as A. Not K for 9 times 10 raised to 9. Just K. You will still see it because by Saturday, I will teach you everything on capacitor. It will make sense to you. So if I know this E now, this E that you are seeing, permittivity, is equals to one, and then ER. This is permittivity, shaping of medium. This one is permittivity of free space. This one is permittivity, relative permittivity, or you call it dielectric permittivity. If you don't call it relative permittivity, you call it dielectric permittivity. Look at this, I said free space permittivity, relative permittivity. If you don't call it relative permittivity, sometimes they just call it dielectric, but I want you to put for dielectric permittivity. Then this one is permittivity of the medium. Let's talk about what each one is proper so that you understand it. Because we'll still see it when we're doing capacitance and capacitor. I hope you know there's difference between capacitor and capacitance. Okay, we'll still talk about that soon. Now, we know that we've seen this one where they normally tell us that it's 8.85. That is this one. Times 10 raised to the minus square. Shibi, I've told you that whatever they put as the units is something you can get using the formulas. Is it that true? But if it's confusing you, just hold on for you. Now, for this dielectric, what is dielectric? Dielectric is simply, whenever you hear dielectric, this particular thing that they are talking about, whenever you hear dielectric, is simply an insulating material you put in between the surface. An insulating material that you put in between the surface of a conducting material. An insulating material that you place or you put in between, an insulating material that you put in between. Sometimes when it's capacitor, you say capacitor, when it's whatever, but I want you to say conducting material. I said an insulating material placed in between the surface. An insulating material placed in between the surface of a conducting material, or itself a conductor, placed in between the surface of a conductor, however you want to put it. Now, if you know that that is dielectric, do you know that air is also an insulator? Sure you know. We also refer to it as vacuum. If that be the case, it simply means that when I don't have any insulator, there are so many insulators. When I don't have any insulator placed in between, let's say I have something like this. Your secondary student told you about capacitor. Let's say I have something like this. Welcome. This thing that I have here, is something that if I want to check it from the side view, it's the same thing I say I have one side like this, I have another side like this. When I'm not looking at it 3D, like I see a part of it straight, a part of it, like I'm looking at it like this, there's this opening. If I don't put any insulating material in between, air will do the insulation for me. Air is in between. But you know that if you make the mistake of trying to make these two things touch each other, what will happen? There will be spark. Or sometimes if you on your gen, if you want to know what I'm saying, for those of you that use gen, if you on your gen, you see that if you go to the wire of your gen, and maybe there's an opening, a cord, that cord is touching a metal, not your gen, touching a metal before you plug it inside. What will happen is that your light will be shaking. Each time that particular opening of the wire touches that metal, the light is shaking because there is spark. So for that same reason, if you make the mistake of not giving space between two conductors, there will be problem. So it's why we space it using them, or we put that insulator. So that insulator you put is what we call dielectric. If it's not there, we say that air is the dielectric there. So if that be the case, when air is the dielectric, we say that E naught is this thing. When air is the dielectric, we say that E naught is this thing. This thing we normally say is a constant. It's because of the fact that the dielectric there is 1. That is air or a vacuum. So that is when you have this. But the minute the dielectric is not air or vacuum, it's not an insulator, this value will change. This thing value will change because it will not be dependent on whatever value the dielectric has. See, in this case, this is E naught equals to E naught for air times 1. So that E naught will be equals to E naught. Is it not true? in this case. So this E naught now at this case is equals to this. And in that case, it simply means that this is equals to E naught. Permittivity is simply equals to E naught when it's N. But the minute there is an insulator in between, watch, the formula will now become in such a way that you now have to get this now will now become E naught equals to E over E R. Very important to note. And if that be the case, notice that whatever dielectric you have will be constant, because whatever material insulator they are giving you, that is why when we start doing capacitor, we give you certain ones to note. Every insulator has its own dielectric. It's not something that you just manufacture. So will be there. Then in that case, you will now be given the permittivity of that medium because of that dielectric there. In that case, you are not finding the permittivity of the free space. Are you getting it now? And the situation whereby, let's say, you are finding this one, E, and you are giving permittivity of free space, and you are giving an insulator that is not N. E now will be the same thing as saying E equals to the same thing as E naught E R. But just that when you are doing this now, there will be value for it. Are you aware? Yes. And notice that because this one is changing, whatever I'm having here will definitely change. So what I want you to take away from that is that this thing that you normally see as a constant is constant because most of the things we are treating is considered that we are using air as our dielectric or vacuum as our dielectric. So we still do more on that when we do capacitor. Don't miss Saturday class. I plead with you. So if I note that means we've touched permittivity of medium, permittivity of free space, relative permittivity, which is also called dielectric. So let's use time and remember it's just revision we are doing. So we say characteristics of electric field, and I've given you some. So let's try. Okay. First of all, electric field is characterized with electric field line. Because you don't see what electric field looks like. It's the electric field line you use to describe what is happening in an electric field. So for that reason, if I have this to be, for example, positive, and I have this to be negative, it simply means that whatever thing I'm using like this to show you this, whatever thing I'm using to show you this, is electric field line. You say that there are imaginary lines. There are imaginary lines used to show the direction of charges in an electric field. There are imaginary lines used to show, that is electric field line. There are imaginary lines used to show the direction of charges in an electric field. So the first characteristics of electric field is simply the fact that it is characterized by electric field line. You don't know what electric field is. You don't know the direction if you don't have electric field line. That is the first one. The second one is that charges in an electric field emanates from the positive terminal and terminates at the negative terminal. So most of the time I give you all these characteristics, but now we are trying to document it so you get it. So charges in an electric field originate from the positive terminal and terminates at the negative terminal. If you don't use terminal, you can say at the negative charge. That's the second one. The third one is that electric field strength describes electric field. If you say, what is your name? You say Peter. I say, okay, Peter, It's just the same way with saying electric field. There is nothing else. But the minute I now start to say, okay, how strong is this? How is the force acting on the charge in that electric field? That's the electric field strength. That is who you are, not your name. So electric field is like a name of a region that is created by source charge and where a test charge is experiencing that electric force. So, but once we are now going into electric field strength. It is what describes electric field. So we say that electric field is described by electric field strength, or we call it electric field intensity. That is the third one. The fourth one is that the movement of charges in an electric field, is spherical. The movement of charges in an electric field is spherical. So you cannot have it that you are defining this and you are putting it as straight line. There are so many of them, and I will try to see that we get to all of it. So the movement of charges in an electric field is spherical. The next one is that a source charge, which is the bigger charge, often creates the region which we call the electric field. A source charge, which is often the bigger charge, creates the region which we call the electric field. While the smaller charge, which is the test charge, experiences the force, the electric force in that region, which you can open bracket and write electric field. So I said a source charge, often the bigger charge, creates the region. A source charge, which is the bigger charge, creates the region. While a test charge, or the smaller charge, experiences the force in that region. So if you note that, I think the last one I will give you, there are so many of them, you go and make your research, there are like 1 million of characteristics for electric field. But these ones I'm giving you are key ones that we are definitely going to be making use of as we progress in this course. I want, as we treat this course, I don't want us to miss any one thing in this our second semester physics. I want to make sure that everything we are doing second semester physics, we miss nothing. Like, we covered every detail. If you've been following the class, you see that we are trying. If you've checked our YouTube videos this semester, you see we are trying, and definitely we do justice to everything. So the last one. Okay, please, when you do that, that one that I just finished is created by a source charge, and then test charge experiencing it. Okay. The last one is that electric field, the force in an electric field, is equals to QE. The force in an electric field is equals to QE. The force in an electric field is equals to QE. So please, if you remember when I told you, when you have to deal with a charge, the force on a charge normal is given by Coulomb's law. But the minute you're talking about this force in an electric field, this is what you should be looking at. So whenever you are treating this course as we progress, deal with me. Have it in mind that you need to put yourself in a situation where you are saying, if it's normal, this is the formula I'm using. Then if it's in electric field region, this is the formula I'm using. Just like you, if you are hungry, how you behave is different. If you are sick, how you behave is different. If you are happy, how you behave is different. It's the same thing with this one. So for that reason, it is something as every day. So when you go on, I believe there are so many characteristics that you still find at that. So please, these characteristics and properties, they are the same thing. When you go home, make research on that. So electric field lines, I said there are imaginary lines that describe the direction or movement of the electric field. Or you said that describe the movement of charges in an electric field. Okay. Then the next one is attraction and repulsion due to field lines. Please, tomorrow's class is math and physics. Math will start first. After math, we are solving all the questions in chapter 2, all the exercise questions in chapter 2 of our physics textbook. So attraction and repulsion due to field lines. Please, positive and negative, what happens to it? They attract. What about positive and positive? This is attract to watch. This one, did you say this one does what? Okay. Minus on top. Okay. Show you that anyhow I place this one. Minus plus is the same thing now. Okay. If I know that what type of force do you think this particular charge will have? Let's say I have a positive charge here and a negative charge here. Notice that charges are not like this, so sure you know. When we do this thing, it's more like using diagram to show the connection. Normally we know that what will be moving there for the field to the spherical shape. But if I have charge here and I have another charge here, if I ask you what type of force will be here, is it a repulsive force or an attractive force? Class, what type of force will I have here? Why? Sherry, positive, negative. That means I should have an attractive force, right? Yes. Well, let's check something. If I say this is the source charge and this is the test charge, if it's attracting, which one? Like, where is the force? Which direction is the force moving? Like this, Sherry? Yes. That means the force is actually going like this. Is it not true? Yeah. Notice something. The force is going like this because the source charge is here. Is it not true? It is something that we can control. It's something we can control. Control in the sense that if I place this thing here, I can say, since this is a charge, this is a charge. What if I carry it and come and place here? And carry this one and come and place here? Is it not true? So for that reason, we know it's an attractive force. But because of the fact that it is moving in this direction, any force that is moving backward like this, we represent it with minus F. You get the point? So if it is placed this way, don't come and argue it. Just have it in mind that the force, the F you are having is going to be minus F. So note that. My friend, do you have class? Lectures. Which is what level? Okay. Please, I think we will. Okay, God wants us to move to geology and mining block. What's the time? Well, please, let's stop here. We start tomorrow.